Hello everyone and welcome. In this video I'm going to talk about binary search trees. So first of all, what is a tree? So a tree is made up of nodes that can be connected into branches. So for example, this is a tree, this is also going to be a tree with only one branch, and this is also a tree, right? So all of these are going to be trees. Now today I'm going to talk about a very special type of trees, which are binary search trees. Now these trees are called binary because every node or every element of the tree can have at most 2 children. So if you look here at the root, which is basically the top node of the tree, it only has 2 children, right? Left and right. Now if you look here at 45, for example, it only has 1 child here, 40. And if you look at 18, 23, 2, and 9, these are going to be leaves because they have 0 children, all right? So that's why this tree is called binary. Now, it is also called a search tree because it has a very important property. If you look closely here at the root once again, and you look to the left, you can see that its left child is smaller than the root, and the right child is going to be greater than the root. And this is true for every node of our tree. And essentially what this means is that the whole left subtree of my root is going to have elements that are only smaller than the root, and the whole right subtree is going to have elements that are greater than the root. And this, like I said, is true for every element of the tree. And this really facilitates the process of searching for elements in our tree. So for example, if you want to search for the element 9, how do we do that? Well, we're going to start here at the root. Now 9 is smaller than 20, right? So we know that the whole right subtree can be eliminated, right? Because all of these elements are going to be greater than the root. So we go to the left here. Now 12 is greater than 9, so we go to the left again. And now 8 is smaller than 9, so we go to the right and we have found our element, right? So that is how you search for elements in the tree. And as you can see, this is a very efficient way to do this. Now, in order to insert an element into the tree, it is the same process, right? So for example, we want to insert 22 here in the tree. This is always going to be inserted here at the bottom of the tree, right? So how do we do this? Well, we start at the root. The root is 20. It is smaller than 22. And so we go to the right, right? Because 22 is going to be greater. It has to be at the right of the root. Now for 32, 32 is greater. So we go here to the left. And now 23 is also greater, so we're going to put 22 here at the left of 23, and we have successfully inserted 22 onto our tree. Now, in order to remove here an element, it is a little bit more complicated, and we're essentially going to have 3 possibilities here. So either the node we want to remove is going to be a leaf, so it doesn't have any children. So for example, if we want to remove 2, it doesn't have any children, all we have to do is grab it and remove it from the tree, right? Really easy. Now the second option is the node we want to remove has 1 child. For example, if we take here 45, how do we remove 45? Well, that's really easy. We grab the child, we exchange it with the node we want to remove, so 40 goes here, 45 goes here, and then we grab the node we want to remove and we just remove it. And there we go, we have removed 45. Now the third option, our node is going to have 2 children. So this is going to be a little bit more complicated. So for example, how do we remove here 32 from our tree? Well, we're going to grab the left subtree here of 32, and we're going to find the greatest element in the left subtree. That is going to be 23. So we're going to grab 23 and we're going to exchange those 2. So 32 goes here, 23 goes here. And now, as you can see, this is one of the previous cases that we've talked about, right? Leaf, or it has 1 child. Now, in this case, it has 1 child. So how do we remove an element with 1 child? We grab the child, we put it in the place of the element we want to remove, and then we remove the element. And this is how we remove an element with 2 children. So now I'm going to talk about traversal. So traversal is essentially going through every node of the tree in a certain order. And there are 3 ways we can do this. We can do this pre-order, in order, or post-order. So let's start here with pre-order. So pre means before, right? So essentially what this means is for every node of a certain subtree, we're going to visit first that node before we visit its children. So the order here is going to be the root of the subtree, then we're going to visit its left child, and then we're going to visit its right child, right? So what will this look like? So first we're going to go to the root. So we're going to visit the root first. I'm going to write here 20. Then we're going to go to the left side. Now 12 is going to be the new root of a new subtree. So we're going to visit the root first, and then we're going to visit the left side. Now 8 is a new root. We're going to write 8 right there. And then 2 is the new root now because we went to the left. Now 2 doesn't have any children, so we go back up to 8. So 8 is the root of this subtree. We've already gone to the root itself. We've already gone left. And now we're going to go right, which is 9, right? So now we have visited this whole subtree. So we're going to go back to 12. Now we have this subtree. We've already gone left. We've already gone to the root. And it's time we go right to 18. Right, so we go to 18 here, and then we're going to go to the root again. And we have already visited the left side. We've already visited the root itself, so we go to the right. Now 32 is the new root of this subtree, so we're going to visit 32 first. Then we're going to go to the left of 32, which is 23. It doesn't have any children, so we just write 23. And then we go to the right of 32, which is 45, right? So this is going to be the pre-order traversal. So first we're going to go to the root, then we're going to visit the left subtree, then we're going to visit the right subtree. Now in order, first we're going to visit the left child, then we're going to visit the root itself, and then we're going to visit the right child. And you will see in just a moment why this is called in order. So first we go to 20. And the first thing we do when we get to the root of a new subtree is visit its left child. We go to the left again here, and we go to the left. We can't really go to the left anymore, so we visit the root, which is 2. We can't really go to the right, so we go back up to 8. Now for this subtree, we have already visited the left, so we go to the root itself, which is going to be 8, and then we go to 9, which is right. And we're going to go back up to this subtree where 12 is the root. We have already gone to the left, so we go to the root itself, and then we go to the right, which is 18. Now we go back up to the main root, which is 20. We have already visited the left subtree. We visit the root itself, and then we visit the right. Now here we're going to visit first the left, so we're going to go to 23. Then we're going to go to the root itself, which is 32. And then we're going to go to the right child, or the right subtree, which is 45, right? And as you can see, this is going to give us the elements in a sorted manner. If you do this in the other way around, so in the other direction, you're going to get a descending order. Like this, we got an ascending order, and this is why it's called in order. Now for the last one, post order is called post because the root is the last thing we're going to visit. So first left, right, and then the root. Right, so we're going to start here at 20. We go to the left, we go to the left, we go to the left. And here, before we go to the root, which is 2, we go to the right. Now there's nothing to the right, so we just go to the root itself. Now we go back up to 8. We went to the left already. Now we need to go to the right, which is 9. And then we go to the root itself, which is 8. Then we go back up to 12. We have gone to the left. Then we need to go to the right, which is 18, and then we go to the root itself, which is 12. Then we're going to go to 20 again. We have already visited the left side, so we go to the right. Now for 32, first we need to go to the left, which is 23. Then we go to the right, which is 45, and then we go to 32 itself. And now for the last element here, it's going to be 20, the main root here of our tree. So this is how you traverse a tree. So essentially how you go through every node of the tree in these 3 different ways. Now the last thing I want to talk about is going to be time complexity. So on average, searching in a tree is going to take log of n time, in which n is the number of elements in the tree. And the reason for this is that every time we go to a new branch of the tree, we're essentially eliminating half of the tree. And this is going to result in a log of n time, right? Log of base 2. However, in the worst case, we're actually going to end up with an O of n. Why? Well, let me give you an example of a tree that looks like this, right? We only have one branch, and we have here n elements. If we want to search here for the last element of the tree, we're going to have to go through every single element of the tree before we find it. So for that reason, we're going to have, in the worst case, a time complexity of O of n for searching in a binary search tree. So that is all I wanted to show you today. Thank you so much for watching. If this video was helpful and valuable to you, please like and subscribe to support the channel, and I'll see you in the next video.